Let's talk about the star schema, which we are going to use also for your assignment 3. So the star schema is the data modeling technique that we use for multidimensional data modeling that is mainly used for data warehouses. There are 3 main components: facts, dimension, attributes. So facts and dimensions are exactly like the tables that you had in ER modeling, okay? So they are both tables, but they are different types of tables. So fact table is storing your subject of analysis. For example, if you want to like measure total sale, then that is sale would be your fact table, right? And then your dimension tables providing just more context to that subject. For example, if your subject is sale, what could be the dimensions tables? Which table do you think are giving relevant information to analyze sale? You can ask, for example, you can think about questions that you may ask when you want to analyze sale. Yeah, time information, right? So that is one important dimension, is time. How about customer information? Is that relevant? Yes, that is relevant. How about location information? Could be relevant too, right? We may want to, like, for example, a business may want to see its sale across different regions, want to analyze sales in different times, right? So time, location, or for example, per customer or per product, right? So want to see which products, for example, had higher sales, which ones had lower sales, and so on. So those are the relevant dimensions, right? And then you have attributes, the same as attribute in the context of the databases that we have seen before. So they are just providing some characteristics like for these dimensions or facts. So for example, if your table or like fact table or your dimension table is product, then the attributes are product name, price, and so on, right? So one important thing is that the distinction between fact table and dimension tables, because when you want to design your star schema, you want to first start by identifying what is your fact, right? So you always look at what do you want to measure, what is the measurement or your subject of analysis, and then that would be your fact table. For example, if the subject of our analysis or if what we want to measure is, for example, total sale or something like that, then that sale would be your fact table. So fact tables contain measures related to the subject of analysis and the foreign keys, associating fact tables with dimension tables. The same way that we connected tables in ER modeling using foreign keys, here we connect tables using foreign key too. The only difference is that it's much simpler now. Instead of thinking, so because when you were like designing ER models, you knew you have some entities, like for example, let's say you had a student, course, enrollment, and so on, right? But sometimes maybe you were confused which tables I have to connect to each other, which tables, like for example, should I connect the student, for example, to instructor or not, and so on. Here, you just don't have to bother yourself. You connect all dimensions to your fact table if it's a single fact. So you have, for example, fact table sale, because the idea of data warehouse is for analytical purposes, right? You want to analyze sale. So whatever dimension table that you have are the tables that are relevant to the sale, such as product, such as customer, such as time, such as regions or locations, right? And so you have to connect all these tables to the fact table. How do you connect tables? Same as before, using foreign keys, right? So you just connect them using foreign keys. And the measures in the fact table are typically numerical and are intended for mathematical computation. That is typically numerical. It may not be, but most of the time. So numeric measurements that represent a specific business aspect or activity, normally stored in fact table that is center of a star schema. That is, you have something like this always. So a star schema looks like this. So you have a fact table here, right? And then you have several dimensions. And do we have any limit for the number of dimensions? No, no limit. So as long as those dimensions are relevant and are actually existing in our database, because we don't want to, like, let's say if you don't have location information, so you cannot like add a location dimension, right? So first of all, they should exist in your operational databases. Second of all, you have to see whether they are relevant or not. Now your fact could be, for example, sale, right? And then the dimensions could be product, because we may want to analyze sale per product. We may want to analyze sale trend, for example, by time, by location, by customer, and so on, right? And you don't have to think about, okay, now let's connect time to customer, customer to product. No, everything is connected to the fact table. Because here, you just want to analyze sales, okay, which is your fact. And so all of them are connected to the fact table. Can you tell me what is the relationship between the dimension tables and fact table? Is it one-to-one, one-to-many, or many-to-many? One-to-many, right? Why? How is it one-to-many? Is it like this or the opposite way? So can you explain what does that mean? For example, each product is related to multiple sales. Each sale contains multiple products, or vice versa?
Can you repeat it?
Yeah. So we want to see what is the relationship between fact table, which is in the center of your analysis, and then we have several dimensions, right? So just a review. We say, for example, this is, let's say, a student. This is instructor, okay? Let's say my assumption is that each instructor can advise multiple students, one or more students, but each student can have only one advisor. Let's say this is the assumption. Then this relation is one-to-many, right? So if each student can have only one instructor, where should I put the one? Here, right? And each instructor may advise many students. Now, you have to think about it in terms of your fact table and dimension tables, because you were correct, they have like many-to-one relationship, but what is the direction of that relationship?
It's the opposite way. So one product can be in many sales, and one sale can contain many products.
What you mentioned is many-to-many then. So think about it. And we'll reach to the slide. I just want you to think about that before. So we said that facts contain numeric measurements that show specific business aspect or activities, such as, for example, sale, and they normally stored in fact table that is the center of a star schema, which I showed you here. And then they contain facts linked through their dimensions, metrics, or fact computed at runtime. Okay. And then dimensions are just providing context to the fact, right? For example, if your fact is sale, then your dimensions could be product, customer, time. These are the relevant information that you may need for like analyze sale, okay?
Fact has like many dimensions, right?
One fact has many dimensions, yeah. And but it doesn't mean that. I mean, you have to think about it like this way. For example, does each sale, include, for example, one product or many products, and the vice versa? And Dimensions are stored in dimension tables, like what I showed here. And the columns in dimension tables contain descriptive information that is often textual. That is not always. So you may have also numerical information. For example, in the product table, you have product name, description, color. So these are descriptive or textual information. But you may also have, for example, product weight, right? Or price. So those are numerical. And in the attributes, the same as what we had before. So here you can see, just let's see the multidimensional data one step further by checking the attribute hierarchy, okay? How many dimensions do I have here? 3 dimensions, thanks for your attention. So we have time dimension, product dimension, and then location dimension here, okay? So the good thing with multidimensional data modeling is that you can analyze your fact through different dimensions, right? And so for example, we can, and also each of them can have like hierarchies as shown here. For example, you can analyze time based on different levels of granularity, such as, for example, yearly, quarterly, monthly, and weekly, right? For example, quarterly could be Q1, Q2, Q3, Q4, right? And then also for product dimension, again, we have some hierarchies, right? For example, product can be grouped into different levels, such as all products, for example, by product type, or one product, depending on the level of your analysis and what you want to analyze, what is your question, then you could use like these different hierarchies. How about location? Location is also structured like from, for example, broad to like narrower. For example, you can have like regions, a state, city, a store, and so on, right? And why are these hierarchies useful? Sorry?
I guess filtering
Filtering
like the product.
products. So what does that mean?
It's like, what I'm trying to say is like optimizing your search into categories.
Yeah.
So like we may want, we may have like different goals for analysis.
We're just extracting like data, like for example, you want the yearly data, or like you want to see your business doing month to month.
Yeah, so as I mentioned, you want to like analyze based on different dimensions, and these hierarchies allow you to have like different, to analyze them on like different hierarchies, right? So for example, let's say your company want to analyze, for example, quarterly sales performance. So you have quarterly information here, right? First, they look, for example, at total sales that you have, for example, at quarter 1, quarter 2, 3, and 4. And then, for example, they may notice that in Q3, you had like a dip in sales, okay? And then you say, okay, so let's drill down into the monthly data now. And then you go, for example, to the monthly data, and you see that, for example, your sales dropped in, for example, the month of, I don't know, November, okay? And then, so you can drill down further by, for example, the region, like by different locations that you have, region, city, and so on, to see, for example, where specifically that drop in sale happened. So that gives you, like, that allow you to aggregate or actually drill down into your data based on like different level of details that provided here. And it kind of also improve our query performance, right? Because we have like, now we have pre-aggregated data. If you remember the slide that we had here, I already mentioned the difference. So here, as you see, we already have some aggregated data here prepared, which gives us much faster query compared to like using like aggregations on like these tables and joining tables and so on. And this was just in a very simple, small database. You can imagine like in larger databases, it would be even more helpful. And as I mentioned, you always have to ask 2 questions when you design your star schema if you want to define your fact. So for a fact table, first ask yourself, what is the measure of your analysis? So for example, you say, I want to analyze, for example, sale, so that is your fact. And then there are two questions that you want to ask before you add any dimension to your star schema. So first of all, the same way as I did here, for example, I said my analysis is on sale, and then one by one, we have several tables, right? For example, we have product, customer, and so on. We don't just put any table that you have in your operational databases into data warehouse. Sometimes we may also combine data from different tables, having a new one here. But for the sake of simplicity, for now, focus on the relevancy of each of like these tables. For instance, we added product as one dimension to the sale because the answer to both questions here is yes. First, can the dimension table be useful for the analysis of the chosen subject? Can, for example, product be useful in analyzing sale? Sure, we may want to analyze the sales, for example, for different products, right? And so that is useful. The second question, can the dimension table be created based on existing data sources? Do we have product information? Yes, we have. Our operational database included the product table, so we also have product information. And so we can have product dimension. So in star schema representation, back to the question I asked you, facts and dimensions are normally represented by physical tables. That is the actual tables that we had before, we have here. And the fact table is related to each dimension through many-to-one relationship, okay? And same as before, they are connected through the foreign keys, right? For example, here is your fact table. As you can see, there are several attributes for each of like these tables, right? But the minimum number of attributes that you can have in your fact table, what is the minimum number of attributes that you can have in your fact table? Yeah, the number of dimensions that we have here, because all dimensions are connected into this fact table, right? And all their primary keys are going to be added as foreign key here. So at least, let's say if we have 4 dimensions here, we should have at least 4 foreign keys or 4 attributes in the fact table, plus some other attributes that it may have. So here you can see the relationship. So the relationship is many-to-one. The relationship between fact and dimension is many-to-one, which means, for example, each of like these sales information that you have in your fact table are related, for example, for one location, one person, one time, one product, right? For example, the relationship between sales and product is many-to-one because each of like these sales record belongs to a single product, okay? But a single product can appear in multiple sales, right? So that's why it's many-to-one. And so here is the example that we had here. We have a sale as a fact table, and then we connect our fact table to all the dimension tables. How do we decide which are our dimension tables? Based on whether they are relevant for our analysis or not. Second, based on whether we have that information in our database or not. For instance, we could add location as a dimension because we may want to analyze sale in different locations, right? And also we had location information in our database. We may want to analyze sales per person. We may want to see, for example, what was the amount, for example, sold to a specific, for example, purchased by a specific customer last year. So we may need, for example, person information. Customer information is relevant. Time information is very relevant because it's mainly like we want to analyze historical data and seeing trends, right? That's the main idea of data warehouse. And so time information is also relevant. And then product information, of course, is important because we want to see, for example, what was the sale per product as well. And here is just an example that I'm going to explain today. So it's a Zagib database. I'm not sure if you have seen your hands-on. I uploaded a SQL hands-on file a few days ago, which contains this example with a lot of queries, like a few queries just for you to practice SQL using this database. So this database is based on your textbook, and it's named Zaggy Retail Company Sale. And so I just call it Zaggy database, okay? So this is just the ER diagram representing a retail sale database for Zaggy database, and it just captures operational data in a normalized format, right? Now, what are the key entities here? We have product, regions, store, sale transactions, category, customer, right? So these are your main entities. So this is just your ER model. Now, this is just to review what information we have in our operational database in this example, right? And then this is just your relational schema. So these are going to be your tables. We have product, vendor, category, customer, transactions, stores, regions. So these are the information that we have. Are these normalized? Are these tables normalized? Yes. And here, the number of items field that you have, here, the number of items can be used as a fact, right? Because it's a measurable value that you may want to analyze. So that is, for example, one thing that you may use, for example, for a fact. And for your assignment, it will be more clear. So it depends on what you want to analyze, right? So as I mentioned, if you want to analyze sales, sale would be fact. If you want to, for example, see the number of items, then that would be your one of the facts. And so here is one dimension, which is the product, because that is relevant, right? We want to see, for example, how many items from like this product were sold, for example. And so we try to build the star schema using ERD plus next session. So today I focus on explaining how you do it and going through the example. And next session I provide more examples for you. So we take the relational schema, convert it to a star schema, okay? So this is very similar to the relational schema that you have, okay? But you want to like aggregate some data, right? Otherwise, why are we going to use data warehouse or a star schema? We are just using the operational databases. The goal is that we want to like have faster querying, trend analysis. So we have to maybe aggregate some of those information or like not including. So we want to just add those dimensions that are relevant. So we create a central fact table, which is sale here, and we connect it to dimensions such as product, calendar, store, and customer. And then as you see here, each of them have also some attributes. Your fact table have at least like these 4 attributes, which are the primary key of the 4 dimensions. Plus, we also have dollars sold and units sold, which shows the total amount of that product sold and also per unit. Now, you can see now the populated star schema where data has been extracted and transformed into like this OLAP ready structure. So here, as you see, you have 5 tables, right? So here you have the same 5 tables. Now, one of these is your fact table, which is here, your sale fact table. And then here you have other dimension tables. Same as what you had in your database assignment. You are asked, for example, to enter some data for the tables that you were creating for your star schema. So that is what I mean. So you just populate them with some information, okay, with some data. Now, if you see here, each sale transaction has keys linking it to the dimension tables, which allows you to query, for example, total sale, for example, by a specific store, right? Or, for example, what was the customer purchase trend over a specific period of time? And what was, for example, the sale of a specific, for example, product category. and so on. So looking at this fact table, you see that we have a lot of useful information. So for example, you can see the dollar served and units sold per customer and product, right? So for instance, you have this product ID 3. So let me go one level back. So here we have customer key 1, that is the primary key in the customer table, right? Which gives you customer information, which is, for example, Tina, right? So Tina bought this product number 3, which is here, right? Which is cozy sock. How many? 5, right? You have the units sold and also the amount that he paid in total. And so it's the same, the way that you can look at it is very similar to what you had in relational databases before, but this time we are just putting more relevant information into like your facts and dimension tables, so you can better, you can access them in a more efficient and faster way. And this time, like all the dimensions which are relevant to your fact table, they are directly connected to the fact, right? So you don't need to like join, for example, 3 or 4 tables anymore. So you may need to, you may get all the information that you want either through the, for example, the fact table, or just like, for example, depending on what, for example, dimension that you want to analyze them, you can access them, for example, by linking them into that dimension. And so here are just some characteristics of dimensions and fact tables. A typical dimension contains relatively static data, while in a typical fact table, records are added continually and table rapidly grows in size. That makes sense, right? Because, for example, if your fact table is sales, then it makes sense because the same, for example, customers may make more and more and more purchases over time, right? Although you may have, for example, customers, new, for example, products and so on, but because the same, for example, products can be purchased, for example, by many customers and so on, so this information is just growing, right? I mean, your sale information, which is in the fact table. And in a typically dimensionally modeled analytical database, dimension tables have orders of magnitude fewer records than fact tables. That's just I explained. Now, one thing that I wanted to mention is using surrogate keys that we have that we use for data warehouses. So if you see here, even though we have product, for example, IDs and so on, but we are using a surrogate key that is, for example, product key, store key, calendar key, and so on. First, my first question, what was surrogate keys? What is a surrogate key? Yeah. So that's a type of a primary key that is automatically generated by the system, right? And can you tell me why here we are using surrogate keys instead of why do we use surrogate keys instead of just the primary keys that we had in the table?
Because when a new row is added to a dimension table, you can auto-increment the primary key for it.
Yeah, that's one good reason, because your dimensions may change over time, right? And then if you remember, we said that we are not changing any record, but we are just adding it as a new record. For example, if I change my address, I mentioned that I'm adding a new record with, for example, Mona, my new address, and so on, right? Now, that data, like for example, Mona at this, for example, location and so on, had some primary keys, right? And then here, when I add it again, it has the same primary key, right? While if you use the surrogate key, then it's system automatically generated by the system. So it makes sure that you don't have the problem with the ever-changing data in your dimension tables, okay? So that's one of the reasons. And so that is just make sure that you have like a unique key for like each of these records, right? And for instance, let's say here we have the customer dimension, right? So let's say a new customer is changing, for example, her zip code. As if you remember, what was one of the characteristics of data warehouse was that they are non-volatile, right? We cannot change them. So can I just update the customer, the Tina zip code? No, I cannot. This is a data warehouse. How can I address that? I'm adding another record with the same customer ID, which is Tina, right? And then the new customer zip code. So what is the problem? Now your primary key is duplicated. So we are using a surrogate key here to make sure that we have a unique primary key. Is this clear? Okay. And this is just one example. If you want, you can refer to your textbook, page 251. Example of a query to show you, for example, how this query, for example, would be executed in dimensional modeling with, for example, a star schema, or with a non-dimensional normalized database, okay? And then you can see that the multi-dimensional modeling makes the queries much simpler and more readable and faster. Maybe we'll do it next session that I have more hands-on. And here, to compare dimensional versus non-dimensional databases, as I mentioned before, we have fewer joins, right? Why do we have fewer joins? Why do we need less joins in dimensional modeling compared to the non-dimensional models that we had before? In non-dimensional models, operational databases, we have normalized tables. Now, why do we have less join here? Yeah, you have, everything is connected to your fact table now, right? So all your dimensions are connected to a single fact. So it is reducing the number of tables that you have to join. And also you have some aggregated data, right? So do you remember that the page where I compared the multi-dimensional models with the operational view? And then I showed that, for example, we have now time dimension, location dimension, or customer dimension. And then we had some aggregated data which showed the total, for example, sale per customer, or total sale per each, for example, time that we had. So we also had some aggregated information instead of like using the aggregate functions ourselves, joining tables and grouping them, right? And now 2 additional data sources are added here. So we are seeing the enhanced dimensional or expanded dimension models based on multiple sources. So the additional information is, for example, in the store. If you see the store table or dimension here, you have some details such as the store size, a store system, C-system, and a store layout, which we didn't have before. For customer, for example, we added some demographic information such as gender, marital status, and so on. And so these additional fields that we have like in each of like these tables, you can see that they are just populated with some values. This gives us more answer more queries, right? For example, now we have day of the week, which we didn't have day of the week in our calendar before. In the first example, we didn't have that. We only had, I think, month, year, and so on. Now, adding day of the week allows, for example, comparisons like which, for example, weekday have the highest sale, maybe weekends, right? Or, for example, the store system help understand if, for example, the cashier-based store perform better, or, for example, self-service store perform better. So you can compare the cashier-based with the self-service. And then we have also more customer information. For example, we have customer credit score, right? That could also help you, for example, if you want, for example, segment your customers. And we can have multiple facts in the dimension tables. What I covered so far is that, for example, we had one fact table. For example, we had sale, right, which was our unit of analysis, the subject of analysis. And then we said, okay, dimensions are all the information that are relevant to that subject of analysis. For instance, if your subject of analysis is sale, then your dimensions are product, customer, time, location, and so on. Whatever that exists in our operational database. Second, whatever that is relevant, right? Can you think of a scenario where we have more than one dimension, more than one fact table? You can think about an example where you want to, for example, analyze more than one subject. Can you think of that? For example, in a company, if they want to, what else can they may want to analyze in addition, for example, to sales?
Like company costs, maybe?
Company cost, one example, yeah.
Customer loyalty, like how often if somebody buys something, they come back and buy it again.
Yeah. So there are many things that they may want to measure, right? And so they may want to, for example, have a sale fact table, right? As we mentioned, to, like, for example, tracking the items that were sold, or for example, analyzing which, for example, their, for example, sales trend over time and so on. Or maybe they want to also have like not only sales, but also, for example, let's say return tables, right? They want to, for example, check the refunds and everything. So that could be another example of another fact table. Now, if they want to, for example, have both sale and return facts table, they may also share some dimensions, right? Which dimensions are they sharing? Customer, product, right? Products are refund, products are sold. So they both, if you have another fact here, which shows the returns or refunds, then this can also be connected to product, right? The customer, and so on. Even like the time when the return happened. So when multiple subjects of analysis, for example, sale and returns, can share the same dimension, a dimensional model contains more than one fact table. So a dimensional model with multiple facts is referred to as constellation or galaxy of stars. Galaxy of stars is a good name for it, right? Because we have a star schema, and now we have like multiple fact tables, so now it's a galaxy of stars. So this approach is more efficient because now, instead of having like two different, let's say, star schema, one, for example, for this one connected to 4 dimensions, another one for the sale connected to the same 4 dimensions. So let's have like just 2 fact tables with the same 4 dimensions, right? So this is more optimized. So it allows you for quicker development of analytical databases for multiple subjects of analysis, for example, sales and returns, because dimensions are reused instead of duplicated. So instead of having product, customers, time repeated for example, the return fact and sales fact, let's have both facts with the same dimensions and a straightforward cross-fact analysis. You can also, that allows you, for example, comparing sales versus returns then, right? Now, this is example, again, Zaghi Retail Company Quality Control Database. You can see the ER model and relational schema again. Now, we want to have multiple fact tables this time. Now, our fact table contains sales and defects. Okay, so the company want to like analyze both sales and defects, and they share the same. We use this structure and this modeling, and I mean a star schema with multiple facts. Why? Why did I use 2 facts here?
They share dimensions.
Yeah, because so that is how you can realize you have to use several facts. If you have each fact represent a measure of analysis, right? For example, defects, sales, returns, and so costs, and so on. And so if they happen to share the same dimension, the idea is that instead of like developing separate models with the same dimensions repeated, instead of like having all these duplicates, let's have the same, put them in the same structure like this, where facts are connected to the same dimensions. They shouldn't share all the dimensions though. Maybe some of them, for example here, they share calendar, store, and product, but customer is only related to the sales fact table, right? For example, defects is not related to customers, right? We want to see what are the defects, for example, for the products. And here, the same tables that we have here, these 6 tables, are populated with some data. And in terms of the attributes that you put like in each of them, again, you have to carefully think about the possible questions that you want to answer later, the analysis that you want to make, and then put all the relevant information, right? And so this is, again, the same multiple fact tables. We have sales fact table here and defects fact table here, and these are your dimension tables, 3 of them shared between like these 2 fact tables. And we can have detailed or aggregated fact tables. So there are 2 types of fact tables, and they are different with different purposes. So if you use a detailed fact table, it means that each record or each row in your fact table is representing a single fact. So this is very much detailed. While in aggregated fact table, each record summarizes multiple facts. So let's see what is the difference, and then I'll let you go. So detailed fact table example. Here, we see a detailed fact table. Why is it detailed? Detailed fact table, in detailed fact table, each record represents a single fact, okay? Now, what does each record here shows? A single sale, right? A single fact. Now, for example, look at this one. For example, this customer bought this product, which, for example, has this amount in dollar, and this is the unit sold. And we have also transaction ID and time of day here, right? Now, if you look, the same customer bought the same product, again with the same quantity and the same amount in dollars. The only thing that is different is time of the day and the transaction ID, right? Now, maybe you may want to actually create an aggregated fact table and summarize, for example, your sales by only, for example, let's say product, customer, store, and day, okay? So you only are interested in product, customer, location, and time, let's say. And then you have like these 4 foreign keys here and this information here. Now, in aggregated fact table, if you see here, we have the same customer again and the same product, so customer key 2, product key 5. Now this time it aggregated the data that we had in the detailed fact table, right? Because the same customer bought the same product 2 times in different times, right? And we just want to see how, for example, what was the total, for example, amount that this customer spent on that specific product, okay? So here you see this aggregated information, which is 4 units of that product with the total amount of 600 instead of having like each row representing a single fact. Now we are aggregating like these two rows into like a single row here, okay? The same is, for example, for this one. So amount from the 9th and 11th record in sales fact table in figure 822 combined. So this is also combined from customer 2 on product 6. So here. So combine this one with this one. So it was 250 here, spent 250 here on the same product, and then maybe not even same product, different product, but it's the amount, like the total amount that he spent, okay? It depends on how you want to like aggregate data. And that's it for today. Okay. Do you have any questions? No?